Imagine this. You wake up tomorrow morning, brew your coffee, scroll through the news, and there it is. A headline that changes everything we thought we knew about human history. Scientists have discovered evidence of an advanced civilization that existed on Earth millions of years before humans ever walked upright. Not aliens from another world. Not ancient astronauts. But something far more unsettling. A civilization that lived right here, on this planet, long before we arrived. Sound like science fiction? Maybe. But here's the thing about science fiction. Sometimes it asks the right questions before science catches up with the answers. This is the Silurian hypothesis. And whether it's true or not, the journey to answer it will take us deep into the nature of time, geology, and what it really means to leave a mark on this planet we call home. Let me start with a question that should make you uncomfortable. How do you know that humans are the first intelligent civilization to evolve on Earth? I'll wait. You're probably thinking about the fossil record, about dinosaurs, about the billions of years of life that came before us. And you'd be right to think that way. We've catalogued an enormous amount of Earth's history. We've found bones, we've found footprints, we've traced evolution through countless species. But here's what should keep you up at night. We've only scratched the surface. Literally. The Earth is 4.5 billion years old. Homo sapiens, our species, has been around for maybe 300,000 years. That's not even a rounding error in geological time. It's a blink. A snap of the fingers. If Earth's entire history were compressed into a single 24-hour day, humans would appear in the last second before midnight. The very last second. Everything we've built, everything we've discovered, everything we think makes us special, all of it fits into that final tick of the clock. So here's the uncomfortable thought. What happened in the other 23 hours, 59 minutes, and 59 seconds? The Silurian hypothesis gets its name from Doctor Who, of all places. In that British science fiction show, there was a race of intelligent reptiles called Silurians who supposedly ruled Earth before humans. But in 2018, two scientists, Gavin Schmidt and Adam Frank, took that fictional concept and asked a very serious question. If an industrial civilization had existed on Earth millions of years ago, what evidence would remain? Could we even detect it? Their answer was disturbing in its uncertainty. Maybe. Maybe not. Think about that for a moment. We've sent robots to Mars. We've detected planets orbiting stars thousands of light years away. We've photographed the event horizon of a black hole. But we can't say for certain whether another civilization rose and fell right here at home, beneath our feet, in the deep past. Let me tell you why this is so hard. It all comes down to time and what time does to evidence. You think your civilization is permanent. You look at the pyramids of Giza and think, well, those have been around for 4,500 years, surely they'll last forever. You look at Mount Rushmore and figure those presidents' faces will endure for eons. But they won't. Not on geological timescales. Give it 1,000,000 years. Just 1,000,000. The pyramids will be gone. Eroded to nothing. Mount Rushmore. Smoothed over by wind and rain. The Great Wall of China. Dust. Your smartphone, your car, your house, every building in every city on Earth, all of it will be crushed, subducted, melted, and recycled by plate tectonics. The Earth is not a museum. It's a recycling plant. And it's very, very good at its job. Here's a number that should terrify you. Only about 0.1% of all species that have ever lived have left fossils. 0.1%. That means 99.9% of all life that ever existed on this planet vanished without leaving a trace we can find. No bones, no shells, no footprints. Nothing. They lived, they died, they were recycled into the planet. Now apply that to civilizations. If fossilization is rare for individual organisms, how much rarer must it be for the artifacts of a technological society? Think about what would remain of our civilization in 10 million years. Not much. Maybe some synthetic materials that don't break down easily. Plastics could persist for a while, but even they eventually degrade under heat and pressure. Nuclear waste would leave a signature, certain isotopes that don't occur naturally. But you'd have to know where to look. And even then, you'd need to recognize what you were seeing. The Silurian hypothesis forces us to confront an uncomfortable reality about deep time. Deep time is not like human time. We think in decades, maybe centuries if we're historically minded. Nations rise and fall in hundreds of years. Empires might last 1,000. But we're talking about millions of years. Tens of millions. Hundreds of millions. At those scales, mountains come and go. Oceans open and close. Entire continents drift from pole to pole. The Earth's surface is constantly being destroyed and remade. Rock that sits at the bottom of the ocean gets pushed under continents, melted in the mantle, and eventually recycled back to the surface through volcanoes. It's an assembly line of destruction. So if a civilization existed 60 million years ago, during the time of the dinosaurs, what would we find? This is where it gets interesting. Schmidt and Frank actually modeled this. They asked what kind of geological signature an industrial civilization would leave. And the answer surprised them. The most obvious marker wouldn't be buildings or tools or even bones. It would be chemistry. Specifically, it would show up in the carbon record. When you burn fossil fuels, you release carbon dioxide that has a specific isotopic signature. Carbon comes in different forms, different isotopes, and the carbon from ancient organic matter has a particular ratio of carbon-12 to carbon-13. When you burn it, that ratio shows up in the atmosphere and eventually gets locked into rocks and ice cores. We can see this signature from our own industrial revolution in ice cores from Greenland and Antarctica. It's right there in the layers of ice, a spike in carbon dioxide with that telltale isotopic fingerprint. But here's the thing. We also see similar spikes in Earth's ancient past. Times when carbon dioxide surged, when global temperatures rose rapidly, when ocean chemistry went haywire. We call these events hyperthermals. The most famous is the Paleocene-Eocene thermal maximum, the PETM, which happened about 56 million years ago. During the PETM, global temperatures shot up by 5 to 8 degrees Celsius in just a few thousand years. The oceans acidified. Species went extinct. It was catastrophic. And we still don't fully understand what caused it. The standard explanation involves volcanic activity or the release of methane from the seafloor. Natural causes. But could it have been something else? Could it have been industrial activity from a civilization we've never detected? Probably not. Almost certainly not. But the point is, we can't rule it out with absolute certainty. And that's what makes the Silurian hypothesis so fascinating. It's not about proving ancient aliens built the pyramids or that lizard people ran the Cretaceous. It's about understanding the limits of what we can know about Earth's past. Let's talk about the fossil record for a minute, because this is where people usually object. They say, well, we found dinosaur fossils from millions of years ago, we found ancient bacteria in rocks billions of years old, surely we'd find evidence of a technological species if one existed. And that seems reasonable. But it's not quite right. First, as I mentioned, fossilization is incredibly rare. You need specific conditions. An organism has to die in just the right place, get buried quickly, avoid being eaten or decaying completely, and then get mineralized before it falls apart. Most things that die just rot. They're consumed by bacteria, by scavengers, by the elements. They return to the cycle. Only in special circumstances do we get fossils. And even then, most fossils are from marine organisms with hard shells or bones. Things that lived on land and had soft bodies. We find almost nothing. Now think about humans. We're land animals. We have bones, sure, but they're not particularly durable. And we're relatively rare compared to, say, trilobites or clams. If our civilization collapsed tomorrow and no humans survived, what would remain in 10 million years? Our skeletons would be long gone. Maybe, a few teeth would survive. Teeth are the most durable part of the human body. But you'd have to get incredibly lucky to find them. And even if you did, a few scattered teeth wouldn't tell you much about our technology or our culture. But what about our stuff? What about all the things we've made? This is where it gets tricky. Most of what we build is made from materials that exist naturally. Concrete is basically artificial rock. It'll break down. Steel is iron, which will rust and return to iron oxide, indistinguishable from natural rust. Glass is silicon dioxide, sand. It might last longer, but weathering will eventually reduce it to sand. Even our most advanced electronics are made from elements found in nature. Silicon, gold, copper, rare earth metals. When they break down, they just become part of the geological background. There are exceptions. Plastics are interesting because they're synthetic polymers that don't really exist in nature. They might persist longer. But even plastics degrade, especially under heat and pressure. In a subduction zone, where one tectonic plate slides under another, temperatures reach hundreds of degrees. Pressures are immense. Plastics would break down into simpler organic compounds, oils, eventually just carbon. Could you detect them? Maybe. If you knew what you were looking for and where to look. But it wouldn't be easy. What about radioactive materials? We've created plutonium, we've enriched uranium, we've left radioactive waste in specific isotopic ratios that don't occur naturally. Surely that would be detectable. And yes, it would. For a while. The problem is half-lives. Plutonium-239 has a half-life of about 24,000 years. That sounds long, but it's nothing on geological timescales. After a few million years, it would be gone. Uranium-235, which we use in reactors and weapons, has a half-life of 700 million years. That's better. If a civilization used nuclear power 50 million years ago, we might still detect anomalous ratios of uranium isotopes. But again, you'd have to know where to look. And you'd have to distinguish it from natural variation. Actually, here's something wild. We have detected ancient natural nuclear reactors. In Oklo, in Gabon, there's a uranium deposit that went critical about 2 billion years ago. Natural conditions were just right, the uranium concentration was high enough, there was water to moderate the reaction, and boom, you had a natural fission reactor running for hundreds of thousands of years. We can see the depleted uranium, the fission products, the whole signature. Nature beat us to nuclear power by 2 billion years. So even if we found evidence of ancient fission, we'd have to rule out natural causes first. This is the central problem with the Silurian hypothesis. Every piece of evidence you might expect from an ancient civilization either degrades too quickly or could be explained by natural processes. It's not that the evidence definitely doesn't exist. It's that we might not be able to recognize it even if it does. Let me give you another angle on this. Let's talk about layers. Geology works in layers. Sedimentary rock builds up over time, layer upon layer, like pages in a book. The deeper you go, the older the rock. By reading these layers, we can reconstruct Earth's history. We can see when volcanoes erupted, when asteroids hit, when sea levels rose and fell. It's an incredible record. But here's the catch. The record has gaps. Lots of gaps. Geologists call these unconformities. They're places where millions of years of rock are just missing. Maybe erosion wore it away. Maybe it never formed in the first place. The point is, the geological record is not complete. It's more like a book where random chapters have been torn out. You can get the general story, but you're missing details. Sometimes you're missing a lot of details. If a civilization existed during one of those gaps, during a time when rock wasn't being deposited or was later eroded away, we'd never know. And here's another thing. Where are we looking? Most of our geological studies focus on accessible rock formations. Places where layers are exposed by erosion, by mountain building, by human excavation. But that's a tiny fraction of Earth's surface. The vast majority of the planet's crust is underwater or buried under miles of sediment. We've barely explored it. There could be entire geological formations we've never examined, entire time periods we've only sampled from a handful of locations. If you wanted to hide evidence of an ancient civilization, the bottom of the ocean would be a great place to do it. And that's exactly where most of Earth's crust ends up eventually, pulled down into subduction zones and destroyed. Now, let's get specific. Let's say there was a civilization. Not tomorrow, not next year, but 85 million years ago, during the late Cretaceous. Dinosaurs are still around. The planet is warm. There are no ice caps. Sea levels are high. And somehow, some species, maybe a lineage of dinosaurs, maybe something else, evolves intelligence. They develop tool use, they discover fire, they build cities, they industrialize. They have a couple thousand years, maybe 10,000, of technological civilization. Then something happens. Climate change from their own pollution. A pandemic. A war. Resource depletion. Whatever. They collapse. They go extinct or revert to a pre-technological state. The geological clock keeps ticking. What would remain? Their bones might fossilize, but remember, fossilization is rare, especially for land animals. And if their population was relatively small, concentrated in certain areas, we might never find them. Or we might find them and not recognize them as intelligent. After all, we've found plenty of dinosaur fossils, and we don't assume they built cities. Intelligence doesn't necessarily leave markers in bone structure. Sure, you might see evidence of tool use, where patterns on teeth, muscle attachment points that suggest fine motor control. But you'd have to be looking for it. And you'd have to find a well-preserved specimen. Unlikely. Their cities would be gone. Completely. 85 million years of erosion, of tectonic activity, of recycling. Any trace of buildings would be pulverized and scattered. Even if some structures got buried quickly and fossilized, they'd be unrecognizable. A pile of mineralized rubble doesn't scream ancient metropolis. It just looks like rock. They're artifacts. Same problem. Metal corrodes. Ceramics break down. Plastics degrade. Even if something survived, it would be so altered, so transformed by geological processes, that we wouldn't know what we were looking at. Imagine finding a chunk of rock with some unusual minerals in it. How would you know it was once a computer chip and not just a weird geological formation? You probably wouldn't. So we're left with chemistry. The carbon record. If this hypothetical civilization burned fossil fuels, we'd see a spike in carbon dioxide in the geological record from 85 million years ago. We'd see that characteristic isotopic signature. We'd see evidence of rapid warming, ocean acidification, maybe an extinction event. And you know what? We do see events like that in Earth's past. Not at 85 million years ago specifically, but at other times. The PETM at 56 million years ago. The end Permian extinction at 252 million years ago, the worst extinction in Earth's history. These events involved massive carbon release, rapid warming, and ecological catastrophe. Could any of them have been caused by industrial civilizations? The honest answer is we don't know. Probably not. The evidence we have points to natural causes. Volcanic activity, methane release, asteroid impacts. But here's what's fascinating. The signatures would be very similar. A civilization burning fossil fuels and a massive volcanic province releasing carbon dioxide would leave nearly identical markers in the geological record. You'd need additional evidence to tell them apart. And that additional evidence, the cities, the tools, the bones, would all be gone. This is what Schmidt and Frank meant when they formulated the Silurian hypothesis. They weren't claiming there definitely was an ancient civilization. They were pointing out that we wouldn't necessarily be able to detect one if there was. Our methods have limits. Deep time erases evidence. And that should humble us. Let's think about this from another angle. What if the question isn't whether we'd find evidence of an ancient civilization, but whether we'd recognize it even if we found it? This is a problem in SETI, the search for extraterrestrial intelligence. When we look for alien signals, we're looking for patterns that seem artificial, that couldn't be produced by natural processes. But we're limited by our imagination. We're looking for the kind of signals we would send. Radio waves. Laser pulses. Mathematical sequences. But what if aliens communicate in ways we haven't thought of? What if their technology is so advanced, so different from ours, that we wouldn't recognize it as technology at all? Arthur C. Clarke said any sufficiently advanced technology is indistinguishable from magic. Maybe it's also indistinguishable from nature. The same problem applies to ancient civilizations. We're looking for the kinds of evidence we would leave. Cities, tools, bones, chemical signatures. But what if an ancient civilization was fundamentally different from ours? What if they didn't build cities the way we do? What if they didn't use metal or plastic? What if they had biotechnology instead of mechanical technology? Living structures, organisms engineered for specific purposes. That kind of civilization might not leave any evidence we'd recognize. Their artifacts would decay like any other organism. Their buildings would look like geological formations. We'd walk right past it and never know. This is speculation, of course. But it's useful speculation because it reminds us that our expectations shape what we find. Archaeologists have a saying, you find what you're looking for. If you're excavating a site looking for pottery, you'll find pottery. You might miss other artifacts because you're not tuned to see them. The same applies on a planetary scale. We're looking for certain kinds of evidence of ancient life and ancient intelligence. But there might be other kinds we're not even considering. Let me give you a concrete example of how easy it is to miss things. In the 1980s, geologists were studying a layer of rock from 66 million years ago, right at the boundary between the Cretaceous and Paleogene periods. This is the famous KPG boundary, the moment when the dinosaurs went extinct. They found something weird. A thin layer of clay enriched with iridium, an element that's rare on Earth's surface but common in asteroids. It was a global layer, found at the same geological moment all over the world. It took years of debate, but eventually, the scientific community accepted that this was evidence of a massive asteroid impact. An impact so large it triggered a mass extinction. But here's the thing. That iridium layer was always there. Geologists had been looking at KPG boundary rocks for decades. They just hadn't noticed the iridium because they weren't looking for it. It took new analytical techniques and a willingness to consider an extraordinary hypothesis, asteroids killing dinosaurs, before anyone saw the evidence that was sitting right in front of them the whole time. Could we be making the same mistake with evidence of ancient civilizations? Maybe there are chemical signatures, isotopic anomalies, geological formations that we've documented but not understood. Maybe we've found the evidence and dismissed it because it doesn't fit our expectations. Or maybe there's no evidence to find. Maybe we really are the first. But the point is, we can't be certain. And that uncertainty is scientifically interesting. Let's talk about timescales again, because I don't think I've adequately conveyed just how much time we're discussing. Humans have been anatomically modern for about 300,000 years. We've had civilization, agriculture, cities, writing, for about 10,000 years. Industrial civilization is only about 200 years old. 200 years. That's nothing. There are trees older than that. There are tortoises alive today that have lived through most of industrial history. Now compare that to the age of complex life on Earth. Multicellular organisms appeared around 600 million years ago. That's 2 million times longer than industrial civilization. 2 million times. If industrial civilization were 1 second, the history of complex life would be 23 days. That's how much time we're playing with. That's how much room there is for things to happen that we don't know about. And it's not just the amount of time. It's what happens during that time. Species evolve, thrive, and go extinct. Continents drift. Climates shift. Oceans appear and disappear. The entire face of the planet changes again and again. 200 million years ago, all the continents were joined together in a supercontinent called Pangaea. If you stood in what's now New York City, you could walk to Morocco without crossing water. 100 million years from now, the continents will be in completely different positions. The Atlantic Ocean will be wider, the Pacific will be smaller, Africa will split along the East African Rift, creating a new ocean. The planet is constantly changing. And every change erases a little more of the past. So when we ask whether there could have been an ancient civilization, we're really asking whether anything could survive this constant recycling. And the answer depends on what kind of evidence you're talking about and how lucky you get. A fossilized bone in a stable sedimentary layer? Sure, that can last hundreds of millions of years. We have fossils from the Cambrian, over 500 million years old. But bones from a single species that existed for a geologically brief time in a limited geographic range? Much less likely. And bones are the most durable things organisms produce. Everything else, tools, buildings, art, it's all far more fragile. There's another aspect to this that's worth considering. Preservation bias. We're much more likely to find evidence of life that existed in certain environments. Marine environments are great for fossilization because sediment accumulates constantly, burying things quickly. Terrestrial environments? Not so much. Things that die on land tend to get scavenged, weathered, broken apart. Only in unusual circumstances, a landslide, a flood, a volcanic eruption, do you get rapid burial and good preservation. So our view of past life is skewed toward marine organisms. We have an incredible record of ancient clams, ancient trilobites, ancient ammonites. But land animals? The record is much spottier. And if a technological civilization arose on land, as ours did, its evidence would be even harder to find. Think about where humans live. We cluster near water, but we build on land. We build on coastlines, in valleys, on floodplains. And these are exactly the places where erosion is most active. Rivers cut down through rock. Coastlines erode. Floodplains get buried and then excavated by later floods. If our civilization ended and geological processes took over, our cities would be destroyed relatively quickly. Coastal cities would be inundated by rising sea levels or exposed by falling ones, then eroded by waves. Inland cities would be weathered by wind and rain, buried by sediment, or uplifted and eroded away. Within a few million years, it would be like we were never here. Except for the chemistry. This is the key insight of the Silurian hypothesis. The most enduring legacy of an industrial civilization isn't its physical artifacts. It's the chemical changes it makes to the planet. When you burn fossil fuels, you're taking carbon that was locked away underground for millions of years and putting it back into the atmosphere. That changes the carbon cycle. It changes ocean chemistry. It changes climate. And those changes get recorded in rocks, in ice, in sediments. They're not easy to read, and they can be obscured by natural variability, but they're there. If we vanish tomorrow, the spike in atmospheric carbon dioxide from the last 200 years would still be visible in ice cores and sediments millions of years from now. Assuming those ice cores and sediments survive, which is a big assumption. Ice caps melt. Sediments get subducted. But in principle, the chemical signature would persist longer than anything else. So if we're looking for evidence of ancient industrial civilizations, we should be looking at chemistry. Isotope ratios. Element concentrations. Anything that seems anomalous, that can't be explained by known natural processes. And we do this already. Geochemists study all kinds of weird spikes and anomalies in the rock record. But they usually have natural explanations. Or rather, we can usually come up with natural explanations. Volcanism explains a lot. So does the occasional asteroid impact. So do changes in ocean circulation, in weathering rates, in biological productivity. Nature is complicated and does lots of things that can mimic what we might expect from industrial activity. That's the problem. It's not that we couldn't detect evidence of an ancient civilization. It's that we might not be able to prove it's from a civilization and not just another weird thing nature did. Let me give you an example. About 2 billion years ago, Earth's atmosphere underwent a dramatic change. It went from having almost no oxygen to having substantial amounts of oxygen. We call this the Great Oxidation Event. It was caused by cyanobacteria, photosynthetic organisms that produced oxygen as a waste product. Over millions of years, they pumped so much oxygen into the atmosphere that it fundamentally changed the planet. It was an environmental catastrophe for most existing life, which was adapted to low oxygen conditions. But it also created opportunities for new forms of life, including, eventually, us. Complex multicellular life needs oxygen. Now, imagine you're an alien geologist visiting Earth 3 billion years from now. You dig through rock layers and find evidence of this massive, rapid change in atmospheric chemistry. Oxygen goes from trace amounts to 20% of the atmosphere. Carbon isotopes shift. Ocean chemistry changes. There's a mass extinction. What would you conclude? Would you think it was natural? Or would you wonder if some ancient civilization had terraformed the planet, engineered the atmosphere to suit their needs? How would you tell the difference? The answer is you'd look for other evidence. You'd try to find fossils, artifacts, something that unambiguously pointed to intelligence. And in the case of the Great Oxidation Event, we have found the culprits: fossilized cyanobacteria, stromatolites, chemical signatures of biological activity. It's clearly natural. But the point is, a dramatic change in atmospheric chemistry alone isn't enough to prove industrial activity. You need corroborating evidence. And if that evidence has been erased by time, you're stuck with ambiguity. This brings us to a philosophical question. What counts as evidence? In science, we usually require multiple independent lines of evidence before we accept a major claim. One anomaly isn't enough. You need several anomalies that all point to the same conclusion. You need a consilience of evidence, different types of data all telling the same story. For the asteroid impact that killed the dinosaurs, we have the iridium layer, we have shocked quartz, we have tektites, we have the Chicxulub crater itself. Multiple lines of evidence all consistent with a massive impact. That's why the theory is accepted. For an ancient industrial civilization, what would we need? We'd need chemical anomalies consistent with fossil fuel burning. We'd need them at a specific time in the geological record. We'd need evidence of rapid environmental change, warming, acidification, maybe extinction. We'd ideally want to find something physical, some artifact or structure that couldn't be natural. And we'd want all of this to be replicable, found in multiple locations around the world. That's a high bar. And honestly, it's probably not a bar we could meet for a civilization that existed tens of millions of years ago. The evidence just doesn't survive that long in a clear enough form. But here's where it gets interesting. What about more recent times? What about 1 million years ago? Or 5 million years ago? The evidence wouldn't be as degraded. We might actually be able to find something. But we haven't. We've studied the geological record of the last few million years in great detail because it's relevant to understanding recent climate change and human evolution. And we haven't found any indication of industrial activity before our own. No spikes in carbon dioxide with the wrong isotopic signature. No anomalous concentrations of synthetic materials. No mysterious structures. Nothing. Does that mean there definitely wasn't an ancient civilization in the last few million years? Pretty much, yes. The evidence would still be too fresh, too obvious. We'd have found it. So if there was a pre-human industrial civilization, it would have to be older than that. Much older. Tens of millions of years at least. Old enough that the evidence has been thoroughly erased or rendered ambiguous. Actually, there's another constraint we haven't talked about. Fossil fuels. Our industrial civilization runs on coal, oil, and natural gas. These are the fossilized remains of ancient life, buried and transformed over millions of years. Coal comes from ancient forests, mostly from the Carboniferous period, about 300 million years ago. Oil and gas come from marine organisms, buried in sediments and cooked by heat and pressure over tens to hundreds of millions of years. If an ancient civilization also industrialized, they probably would have used fossil fuels too. At least initially, before developing other energy sources. Fossil fuels are concentrated energy, easy to extract and burn, at least at first. They're the low-hanging fruit of energy technology. But here's the thing. Those fossil fuels had to exist for that civilization to use them. Which means the civilization had to come after the organic material was buried but before we dug it up. Our coal comes from the Carboniferous. Our oil comes from various times, but a lot of it from the Mesozoic, the age of dinosaurs. If a civilization arose in the Triassic, 200 million years ago, they could have used Carboniferous coal, which would have been mature by then. They could have used older oil deposits. But if they arose in the early Paleozoic, 500 million years ago, there wouldn't have been much fossil fuel available. Not enough complex land plants to make coal. Not enough marine productivity to make oil. They'd have to find another energy source. This actually constrains when a Silurian-type civilization could have existed. It needs to be recent enough that fossil fuels exist, but old enough that the evidence has vanished. That gives us a window from maybe 200 million years ago to a few million years ago. Earlier than 200 million years, there's not enough fossil fuel. Later than a few million years, we'd have found evidence. Of course, they might have skipped fossil fuels entirely and gone straight to renewable energy or nuclear power. In which case, the window is wider. But that seems less likely. Every technological civilization we can imagine, which is admittedly just one, ours, goes through a fossil fuel phase. It's easy energy. You burn stuff. You get heat. You use the heat to do work. It's intuitive. Figuring out how to harness solar or wind or nuclear energy requires a much deeper understanding of physics. It's a harder path. So the fossil fuel constraint probably applies. But even with that constraint, we're still talking about a potentially very long span of time. 200 million years ago to 3 million years ago. That's a 197 million year window. Plenty of time for something to happen. Plenty of time for a species to evolve intelligence, industrialize, and collapse. Maybe more than once. Maybe several times. We wouldn't know. Of course, we have to ask why we don't see signs of those collapses in the evolutionary record. If a species industrialized and then went extinct, we'd expect to find their fossils, right? We find dinosaur fossils. We find fossils of ancient mammals, ancient reptiles, ancient fish. Why not ancient industrial species? And the answer loops back to what I said earlier. Fossilization is rare. If the species didn't have a large population, if they didn't live in environments conducive to fossilization, if they existed for a geologically brief time, we might not find them. Or we might have found them and not recognized them as intelligent. Fossil bones don't come with labels saying, "This one used tools," or "This one built cities." You have to infer that from context. From associated artifacts, from signs of culture, from brain size and structure. And if the artifacts are gone and the fossils are fragmentary, you might not make the inference. There's also the possibility that an industrial species wouldn't look like what we expect. We think of intelligence as requiring a large brain. But that's because we're mammals and we have large brains. Other animals show intelligence with different neural architectures. Octopuses are remarkably intelligent, and their brains are structured completely differently from ours. Most of their neurons are in their arms, not their heads. Birds can be incredibly smart with brains that are tiny compared to mammalian brains. They just pack neurons more densely. So maybe an ancient intelligent species had a small brain by mammalian standards. We'd find their fossils and classify them as just another animal, never suspecting they were the ones who built cities and burned coal 60 million years ago. This is all very speculative, of course. We have no evidence that any of this actually happened. But that's the point. The Silurian hypothesis isn't a claim that ancient civilizations existed. It's an exploration of what we can know and what we can't. It's a thought experiment that reveals the limits of our knowledge. And those limits are wider than most people think. Let's pivot to another question. If we're the first industrial civilization on Earth, are we likely to be the last? That's actually the question that motivated Schmidt and Frank to write their paper. They weren't really interested in ancient lizard people. They were interested in the long-term fate of industrial civilizations. Specifically, they wanted to know how long the evidence of our civilization would last. Because that tells us something about how hard it would be for future scientists, whether human or from some other species, to detect us if we collapse and vanish. Think about it. If humanity goes extinct in the next 1,000 years, if we collapse due to climate change or war or disease or any other catastrophe, what would a future intelligent species find 50 million years from now? Would they know we existed? Would they understand what happened to us? Or would we be as mysterious to them as hypothetical Silurians are to us? The answers are unsettling. They might find some chemical signatures. Elevated carbon dioxide levels in ice cores or sediments from the late Holocene. Plastic residues, though most plastics would be degraded by then. Radioactive isotopes from our nuclear tests and reactors, though many of those would have decayed. They'd probably notice the mass extinction event we're currently causing, the rapid loss of biodiversity. That shows up in the fossil record. But would they attribute it to an industrial civilization? Or would they think it was just another natural catastrophe, like the asteroid that killed the dinosaurs or the volcanism that caused the end Permian extinction? They probably wouldn't find our bones. Not in any quantity. Human fossils are already rare. We haven't been around long enough to leave much of a trace. And most of the places where humans live aren't great for fossilization. We'd be lucky to leave a few scattered specimens. They might not even recognize them as intelligent. Without tools and art and culture, a human skeleton is just another primate. Our cities would be completely gone. 50 million years is enough time to erase everything. The best-case scenario is that some structures get buried quickly in sediment and fossilized. But even then, they'd be so transformed by diagenesis, the process of rock formation, that they wouldn't look like buildings. They'd look like weird rock formations. Maybe a geologist would notice that they're too regular, too patterned to be natural. Maybe they'd wonder what geological process could create such structures. But would they conclude it was an ancient civilization? Hard to say. What about space? This is an interesting angle. We've sent probes to other planets, to asteroids, to the outer solar system. We've left equipment on the moon. We've put satellites in orbit. Some of those satellites are in high orbits where they'll stay for millions of years. The stuff we left on the moon could last billions of years. There's no atmosphere to cause weathering, no plate tectonics to destroy it. Just the occasional micrometeorite impact and solar radiation. But that's slow erosion. In 50 million years, our lunar landing sites would still be there, degraded but recognizable. If a future species reached the moon and looked in the right places, they'd find evidence that someone was there before them. That's actually a profound thought. The most enduring evidence of human civilization might not be on Earth at all. It might be in space. On the moon, on Mars, in orbit around the sun. Our spacecraft, our landers, our rovers. They'll outlast anything we build on Earth. In a million years, Earth will have recycled all trace of our cities, but curiosity will still be sitting on Mars, half buried in dust but essentially intact. That's where a future archaeologist should look. Not in the ground. In the sky. But let's get back to Earth and the Silurian hypothesis. One thing we haven't discussed is the Drake equation of Earth. You're probably familiar with the Drake equation for estimating the number of intelligent civilizations in the galaxy. You multiply together a bunch of factors: the rate of star formation, the fraction of stars with planets, the number of habitable planets per star, the fraction where life arises, the fraction where intelligence evolves, the fraction that develop technology, and the length of time those civilizations last. It's a framework for thinking about SETI. We can apply the same logic to Earth. How many technological civilizations could have arisen on Earth over its history? Let's do the math. Earth is 4.5 billion years old. Complex multicellular life has been around for 600 million years. Intelligence seems to require complex brains, which means complex animals. So let's say the window for intelligent life is 600 million years. Humans took about 600 million years to evolve from the first complex animals. But that's just one path. Maybe intelligence could evolve faster. Maybe slower. Let's say, very roughly, that intelligence could emerge every 100 million years if conditions are right. That gives us 6 opportunities for technological civilizations over Earth's history. Of course, that's wildly speculative. The evolution of intelligence depends on countless factors, most of which we don't understand. It might be incredibly rare, a fluke that happened only once. Or it might be common, almost inevitable given enough time. We don't know. We have a sample size of 1, us. That's not enough to calculate probabilities. But let's play with the idea. If intelligence could evolve multiple times, why don't we see evidence of it? One answer is that we do see evidence, we just don't recognize it. Another answer is that it only happened once, and we're it. A third answer is that it happened multiple times, but the evidence has been erased. The Silurian hypothesis leans toward that third option. Not as a certainty, but as a possibility we can't rule out. Here's another angle. Convergent evolution. This is the idea that similar environmental pressures produce similar adaptations in unrelated species. We see it all the time in biology. Sharks, dolphins, and ichthyosaurs all evolved similar body shapes because they all swim in water. Birds, bats, and pterosaurs all evolved wings because they all fly. Eyes have evolved independently dozens of times because sight is so useful. The details differ, but the general solutions converge. Could the same be true for intelligence? If intelligence is advantageous, if it helps organisms survive and reproduce, we'd expect it to evolve multiple times in different lineages. And maybe it has. Primates are intelligent. Cetaceans, whales and dolphins, are intelligent. Elephants are intelligent. Corvids, crows and ravens, are intelligent. Parrots are intelligent. Octopuses are intelligent. These are all completely different lineages, separated by hundreds of millions of years of evolution. Yet they all independently evolved complex cognitive abilities. So intelligence seems to be something evolution finds again and again. It's a good solution to certain problems. But there's a difference between intelligence and technological civilization. Dolphins are smart, but they don't build cities. They live in water, they don't have hands, they can't make fire. They're limited by their environment and their anatomy. Same with octopuses. Brilliant animals, but they're solitary, short-lived, and aquatic. Not a recipe for technological development. Elephants have the smarts and the dexterous trunk, but they're grazers living in social groups without much need for tools. Corvids are clever, but they're small and short-lived. Humans lucked into a specific combination of traits: intelligence, dexterity, social cooperation, long lifespan, and an environment where tools and fire were advantageous. That combination might be rare. Or maybe it's not. Maybe over 600 million years, that combination has appeared multiple times in different species. We know dinosaurs were around for about 165 million years. That's a long time. Plenty of time for intelligence to evolve. Some dinosaurs, particularly the theropods, the group that includes T. rex and Velociraptor, had relatively large brains for their body size. Some were clearly social, living and hunting in groups. Some, like the Tridentids, had big brains, forward-facing eyes for depth perception, and grasping hands. They looked like they were on the path to intelligence. Did any of them cross that threshold? Did any develop culture, language, tool use? We don't know. We find their bones, but bones don't tell us about behavior. We can make inferences, but they're limited. And here's the kicker. Even if an intelligent dinosaur species existed, even if they built a civilization, we might not be able to prove it. The evidence would be gone. We'd find their fossils and classify them as just another dinosaur. Maybe someday, a paleontologist will dig up a troodontid skeleton and notice something odd. Where patterns on the bones suggesting tool use. An unusually large brain case. Associated artifacts that somehow survived. And suddenly, we'd have to rethink everything we thought we knew about the Mesozoic. But until that day, if it ever comes, the Silurian hypothesis remains just that. A hypothesis. An intriguing, unsettling, ultimately unanswerable question about the limits of our knowledge. Let me bring this back to the present. Why does any of this matter? Why spend time wondering about hypothetical ancient civilizations when we have plenty of real problems to deal with? Because it's not really about the past. It's about the future. The Silurian hypothesis is a mirror. It asks us to imagine how we'll be remembered, or whether we'll be remembered at all. And that has implications for how we act now. If our civilization collapsed tomorrow, if we went extinct or regressed to a pre-industrial state, what would we leave behind? In 100 years, our buildings would start to crumble. In 1,000 years, most cities would be ruins. In 10,000 years, almost everything would be gone, overgrown, buried, eroded. In 1,000,000 years, you'd have to search very carefully to find any trace of us. In 10 million years, you'd need luck and sophisticated geochemistry. In 100 million years, we'd be a mystery, an ambiguous blip in the geological record. Future geologists might argue about whether the carbon spike in the late Holocene was caused by volcanism or by an industrial civilization. They wouldn't be able to prove it either way. That's our legacy if we fail. A question mark in stone. But it doesn't have to be that way. We could choose a different path. We could build a civilization that lasts. Not for centuries, but for millennia. Not for millennia, but for millions of years. We could become a truly sustainable species, one that lives in balance with the planet instead of consuming it. We could spread to other worlds, ensuring that even if Earth's geological recycling erases us here, we endure elsewhere. We could leave messages, time capsules, archives designed to survive deep time. We could make our mark in ways that won't fade. Or we could fail. We could exhaust our resources, ruin our climate, poison our oceans, and collapse into oblivion. We could become the very thing the Silurian hypothesis warns us about. A ghost in the machine. A lost civilization that future scientists, human or otherwise, puzzle over without ever finding answers. The choice is ours. But the clock is ticking. And geological time doesn't care about our deadlines. You know what's really haunting about the Silurian hypothesis? It's not the idea that we might not be first. It's the idea that we might not be last. That if we fail, if we destroy ourselves, life will go on. Evolution will continue. In another 50 million years, another 100 million years, some other species might evolve intelligence. They might build cities, discover fire, split the atom, wonder about the stars. They might even ask the same questions we're asking. Are we alone? Are we the first? And they'll dig through the rocks, trying to understand the history of their planet, and they'll find anomalies. Chemical signatures that don't quite make sense. Carbon spikes. Extinction events. Plastic residues. Radioactive isotopes. And they'll wonder. They'll hypothesize. They'll argue. But they won't know. Not for certain. Because we didn't leave them a clear message. We didn't survive long enough to say, yes, we were here. We existed. We thought, we felt, we built, we wondered. We were real. And maybe that's the saddest legacy of all. Not to be forgotten, but to be doubted. To become a hypothesis instead of a fact. The Silurian hypothesis forces us to confront our insignificance in the face of deep time. We like to think we're important, that our achievements matter, that we'll be remembered. But the Earth is old, and it's patient, and it has a way of erasing things. Mountains rise and fall. Oceans come and go. Entire continents drift and collide. Against that backdrop, a few thousand years of civilization is nothing. A blink. A snap. A moment lost in the vastness of geological time. But here's the thing. Just because something is temporary doesn't mean it's not meaningful. Every life is temporary. Every achievement is temporary. Eventually, the sun will expand and consume the earth. Eventually, the universe will suffer heat death and everything will end. Does that make your life meaningless? Does that make human achievement worthless? No. Meaning isn't about permanence. It's about the moment. It's about what we do while we're here. So maybe it doesn't matter if future geologists can prove we existed. Maybe it doesn't matter if the evidence survives. What matters is that we exist now. That we're asking these questions. That we're trying to understand our place in the universe. That we're curious, creative, conscious beings who can contemplate deep time and our own impermanence and still choose to build, to explore, to learn. The Silurian hypothesis isn't really about ancient civilizations. It's about us. It's about our relationship with time and memory and legacy. It's about the fragility of existence and the resilience of life. It's about the difference between being and being remembered. And maybe, just maybe, it's a warning. A reminder that civilizations can fall. That technological advancement doesn't guarantee survival. That nature always wins in the long run. If there were ancient civilizations, they failed. They collapsed. They vanished. We could too. But we could also succeed. We could be different. We could learn from the past, even if that past is hypothetical. We could build a civilization that endures not through brute force, not by dominating nature, but by understanding it, by working with it, by recognizing that we're part of the system, not separate from it. That's the real lesson of the Silurian hypothesis. Not that we're doomed to repeat the failures of those who came before us. But that we have a choice. We can be thoughtful. We can be sustainable. We can be wise. Or we can be another question mark in the rocks, another anomaly for future scientists to puzzle over, another civilization lost to time. I know which future I'd prefer. Let's dig deeper into the science. Because as fun as it is to speculate about dinosaur civilizations and lost Atlantises, The real value of the Silurian hypothesis is what it teaches us about geology, about the rock record, about how we read Earth's history. This isn't just philosophy. It's hard science. When geologists study ancient rocks, they're looking for clues. Every rock tells a story. The type of rock, sedimentary, igneous, or metamorphic, tells you how it formed. Sedimentary rocks form from compressed sediments, usually underwater. Igneous rocks form from molten magma. Metamorphic rocks form when existing rocks are transformed by heat and pressure. Just knowing the rock type tells you something about the environment where it formed. But the details are in the chemistry. Trace elements, isotope ratios, mineral composition, all of these things vary depending on conditions. Temperature, pressure, the presence of water, the availability of oxygen, biological activity. It all leaves a signature. And by reading those signatures, geologists can reconstruct ancient environments with remarkable precision. They can tell you the temperature of the ocean 200 million years ago. They can tell you when ice caps existed and when they melted. They can track the rise and fall of atmospheric oxygen over billions of years. This is how we know about Earth's history. Not from written records, obviously. There were no humans around for most of it. But from chemical records locked in stone. And those records are incredibly detailed. We can see individual volcanic eruptions from millions of years ago. We can see meteor impacts, flood events, changes in sea level. The resolution isn't perfect, geological processes blur things, but it's better than you might think. Now, here's the question. If a technological civilization existed in the past, what chemical signature would it leave? We've already talked about carbon isotopes from burning fossil fuels. But there's more. Let's think about what industrial civilization does to the planet geochemically. First, mining. We dig up enormous quantities of metals. Iron, copper, aluminum, gold, rare earth elements, all of it concentrated in our cities and factories and products. When those products corrode and break down, those metals get redistributed in the environment in patterns that wouldn't occur naturally. Normally, metals are dispersed evenly through rock or concentrated in specific or deposits by geological processes. But industrial activity creates different patterns. You get high concentrations of metals in specific locations, the sites of former cities or industrial facilities, along with unusual ratios of elements that co-occur in manufactured products. Would this be detectable millions of years later? Maybe. Metal deposits can survive for a long time if they're buried in the right conditions. Archaeologists find bronze artifacts from thousands of years ago. But millions of years? Unlikely. The metals would oxidize, corrode, and disperse. You might get geochemical anomalies, localized enrichments of certain elements, but you'd have to distinguish them from natural mineral deposits. And without context, that's hard. Second, synthetic chemicals. We've created thousands of compounds that don't exist in nature. Pesticides, pharmaceuticals, industrial solvents, plastics, all kinds of things. Some of these break down quickly. Others persist. PCBs, polychlorinated biphenyls, are industrial chemicals that were banned in the 1970s but still linger in the environment. They're toxic and they don't degrade easily. In a million years, though, they'd be gone. Broken down by heat, pressure, radiation, and microbial action. Maybe some degradation products would remain, unusual organic molecules that hint at synthetic origins. But you'd need very sophisticated analysis to detect them, and you'd need to know what you're looking for. Third, nuclear activity. This is the big one. We've detonated hundreds of nuclear weapons, releasing radioactive isotopes into the atmosphere. We've built nuclear reactors, creating plutonium and other transuranic elements that don't occur naturally. We've generated radioactive waste that will remain dangerous for thousands of years. This leaves a clear signature. Elevated levels of isotopes like cesium-137, strontium-90, and various plutonium isotopes. These isotopes have specific half-lives, and their presence in specific ratios is a dead giveaway of nuclear technology. But here's the catch. Half-lives. Cesium-137 has a half-life of about 30 years. In 1,000 years, it's essentially gone. Strontium-90 has a half-life of about 29 years. Same story. Plutonium-239, which we use in weapons and reactors, has a half-life of 24,000 years. That's longer, but still not long enough. In 1,000,000 years, the plutonium would be decayed to undetectable levels. In 10 million years, definitely gone. There are longer-lived isotopes. Uranium-235 has a half-life of 700 million years. If a civilization enriched uranium for reactors or weapons, the altered isotope ratio might be detectable even tens of millions of years later. But you'd have to find the site where the uranium was used, and you'd have to have a sample that wasn't contaminated or altered by subsequent geological processes. It's possible, but it's a needle in a haystack. So nuclear signatures are probably the best bet for detecting ancient industrial activity, but even they have limits. They fade. They disperse. They get buried and altered. After 100 million years, you're probably not going to find them. Fourth, nitrogen. Industrial agriculture relies on synthetic nitrogen fertilizer, produced through the Haber-Bosch process. This takes nitrogen from the atmosphere and fixes it into ammonia, which is then used to make fertilizers. It's one of the most important inventions of the 20th century. It's also completely transformed the nitrogen cycle. We've doubled the amount of reactive nitrogen in the environment. That nitrogen ends up in soils, in waterways, in the ocean. It causes algal blooms, dead zones, eutrophication. And it leaves a chemical signature. Elevated levels of nitrogen compounds, altered isotope ratios of nitrogen-14 and nitrogen-15. Would this be detectable millions of years later? Probably not. Nitrogen is highly reactive. It gets cycled through biological systems very quickly. It's incorporated into proteins, nucleic acids, and other organic molecules, then released when those molecules break down. Some nitrogen ends up buried in sediments, but it's constantly being recycled. The timescale for nitrogen cycling is thousands to millions of years, which is fast on geological timescales. So any nitrogen spike from ancient agriculture would be smoothed out and lost in natural variability. Fifth, ocean acidification. When you pump carbon dioxide into the atmosphere, some of it dissolves in the ocean, forming carbonic acid. This lowers the pH of seawater, making it more acidic. Ocean acidification affects marine life, especially organisms with calcium carbonate shells or skeletons. Corals, mollusks, some plankton. It stresses them, makes it harder for them to build shells, can even dissolve existing shells. Over time, this can cause extinctions and shifts in marine ecosystems. Ocean acidification leaves a signature in the rock record. You see changes in the types of organisms that survive, shifts from carbonate-secreting organisms to those that don't need carbonate. You see changes in the chemistry of marine sediments, alterations in carbon and oxygen isotopes. And you see dissolution surfaces, where carbonate sediments were partially dissolved by acidic water. We see this signature in past events like the PTM. Ocean acidification, ecological disruption, extinction. It's clearly associated with rapid carbon dioxide increase. But is it diagnostic of industrial activity? Not really. Volcanism can cause ocean acidification too. So can methane release from the seafloor. Without additional evidence, you can't distinguish industrial carbon dioxide from natural carbon dioxide. They have the same effect on ocean chemistry. So that's the problem. Almost everything an industrial civilization does to the planet, nature can also do. Carbon dioxide spikes. Volcanism. Ocean acidification. Volcanism. Metal enrichments. Hydrothermal vents. Unusual organic molecules. Biological activity. Radioactive isotopes. Natural reactors or supernova fallout, in principle. For every industrial signature you can think of, there's a natural analog. And over millions of years, the industrial signature degrades and becomes indistinguishable from the natural background. This is why Schmidt and Frank concluded that detecting an ancient industrial civilization would be very difficult. Not impossible, but difficult. You'd need a combination of signatures that, taken together, strongly suggested industrial activity. And you'd need them in a geological context that made sense. A short-lived event, geologically speaking. A few thousand to a few tens of thousands of years. If it lasted longer, it wouldn't look industrial. It would look like a slow natural change. And you'd need luck. You'd need the right sediments to have been deposited in the right places and preserved through millions of years of geological activity. You'd need those sediments to be accessible, exposed by erosion or drilling, not buried miles underground or subducted into the mantle. And you'd need someone to be looking for the signatures, to have the technology to detect them, and to recognize them as potentially artificial rather than natural. That's a lot of ifs. But let's flip the question around. Instead of asking how we'd detect an ancient civilization, let's ask how we'd make ourselves detectable. If we wanted to leave a message for future geologists, how would we do it? What would we build or bury that could survive 100 million years and be unambiguously artificial? This is actually a real problem that scientists have thought about in the context of nuclear waste. We have radioactive waste that will remain dangerous for tens of thousands of years. How do we warn future humans not to dig it up? Language changes. Symbols change. In 10,000 years, English will be completely incomprehensible. Symbols we think are universal, like skulls and crossbones, might mean something different or nothing at all. So how do you create a warning that transcends cultural change? Some proposals involve hostile architecture, making the site physically uncomfortable or foreboding. Spikes, rough textures, oppressive shapes. The idea is to evoke an instinctive aversion. Other proposals involve redundancy, messages in multiple languages and formats. Pictograms, diagrams, maybe even encoding information in DNA and releasing it into the environment. If you're creative enough, you can think of ways to preserve information over deep time. But they're all imperfect. They all rely on assumptions about future people's psychology, technology, and motivations. Now extend that to 100 million years. Forget future humans. You're trying to communicate with a completely different species. Maybe they don't even have eyes. Maybe they communicate through chemical signals or electromagnetic fields. How do you design a message that they'll recognize as a message? It's almost impossible. But there is one thing that might work. Mathematics. Mathematical relationships are universal. If you can create a structure or a pattern that embodies a mathematical principle, something that couldn't occur naturally, that would be recognizable to any technologically advanced species. Prime numbers, for example. Or the digits of pi. Or the Fibonacci sequence. If you could encode these into a durable medium, into the arrangement of isotopes or the structure of a mineral, it would be a clear sign of intelligence. Except that's really hard to do. How do you encode numbers into rock in a way that will survive 100 million years? You can't carve them. Erosion would wear away any carvings. You can't write them. Writing requires a substrate that won't decay. Maybe you could use isotopes. Deliberately alter the ratio of isotopes in a sample to match a mathematical sequence. But isotopes can migrate over time, diffusing through rock, especially under heat and pressure. And even if they stayed put, would future scientists recognize the pattern as artificial? They might just think it's a weird natural variation. It's a hard problem. Maybe an unsolvable problem. Which means if we collapse and vanish, we probably won't be able to leave a clear message. We'll just leave ambiguous clues. And future scientists will argue about us the way we argue about hypothetical Silurians. Some will say the evidence points to intelligence. Others will say it's just natural variation. And neither side will be able to prove they're right. Unless we don't vanish. Unless we survive. That's the clearest message. To still be here. To meet those future scientists and say, yes, we've been here all along. We endured. Let's talk about specific events in Earth's history that might, just might, have been caused by industrial civilizations. I'm not saying they were. I'm saying they have some features that could be consistent with industrial activity if you squint and ignore more likely natural explanations. But it's fun to speculate. The Paleocene-Eocene thermal maximum, the PETM, 56 million years ago. This is the big one. Global temperatures rose by 5 to 8 degrees Celsius in a few thousand years. Carbon dioxide spiked. Ocean acidification occurred. There was a mass extinction of marine organisms. And it all happened very quickly by geological standards. The carbon isotope ratio shifted, indicating a massive release of light carbon, the kind you get from organic matter. Where did the carbon come from? The leading hypothesis is methane hydrates, frozen methane on the ocean floor, which destabilized and released huge amounts of methane into the atmosphere. Methane is a greenhouse gas, so it caused warming, which destabilized more hydrates, a feedback loop. Eventually, the methane oxidized to carbon dioxide, and the whole system took hundreds of thousands of years to stabilize. But here's the thing. We don't know for sure that's what happened. It fits the evidence, but there are gaps. And if you wanted to invoke an industrial civilization, you could. You could say a civilization industrialized during the late Paleocene, burned fossil fuels, released carbon dioxide, triggered warming and ocean acidification, and then collapsed, maybe from the very climate change they caused. Their physical remains were destroyed or subducted. All that's left is the carbon spike and the extinction event. It's a stretch, but it's not impossible. Why is it a stretch? Because the timescale is too long. The PETM took thousands of years to develop. Industrial carbon release happens over decades to centuries, not millennia. So you'd have to assume the civilization lasted for thousands of years at an industrial level, which seems unlikely given our own trajectory. Or you'd have to assume they triggered a feedback loop that dwarfed their own emissions, which is possible but makes them less detectable. The feedback loop would dominate the signal. Also, we don't see other signatures we'd expect. No unusual metal concentrations. No synthetic organic molecules. No radioactive isotopes. Just carbon. And carbon alone isn't enough. So the PETM was almost certainly natural. But it's the kind of event that an industrial civilization could cause. And that's worth noting. Another event, the torsion oceanic anoxic event, about 183 million years ago, during the Jurassic. The oceans lost oxygen, marine life died off, carbon dioxide increased, and temperatures rose. It's associated with massive volcanism in southern Africa, the Kourouferer Large Igneous Province. Millions of cubic kilometers of lava erupted over a couple million years, releasing enormous amounts of carbon dioxide and sulfur dioxide. The sulfur caused acid rain. The carbon caused warming. The warming reduced ocean circulation, leading to anoxia. It was a cascade of environmental disasters. Could a civilization have caused it? Not the volcanism itself. Obviously. But could they have contributed to the carbon dioxide? Could they have accelerated the process? Again, it's a stretch. The event lasted too long, millions of years. Industrial activity is fast. And we have a perfectly good natural explanation, volcanism. But if you really wanted to, you could imagine a scenario where a civilization existed during this time and their activity made things worse. Not the primary cause, but a contributing factor. Their carbon emissions added to the volcanic carbon, pushing the climate over a tipping point. It's speculative, but it's illustrative of how hard it is to separate industrial signals from natural ones when they're both releasing the same thing. What about the end Permian extinction, the Great Dying, 252 million years ago? This was the worst extinction in Earth's history. 96% of marine species went extinct. 70% of terrestrial species. It was apocalyptic. The cause? Again, volcanism. The Siberian Traps, one of the largest volcanic events in Earth's history. Millions of cubic kilometers of lava over a few 100,000 years. Carbon dioxide, sulfur dioxide, probably also mercury and other toxic metals. Global warming, acid rain, ocean anoxia, hydrogen sulfide release from the oceans poisoning the atmosphere. Everything went wrong at once. And yet, there are anomalies. Spikes in fungal spores, suggesting dead forests and decomposition. Rapid changes in carbon isotopes, faster than you'd expect from volcanism alone. Some scientists have proposed that the volcanism triggered a runaway greenhouse effect, methane release from hydrates amplifying the warming. Others have suggested coal burning. The Siberian Traps erupted through massive coal deposits, igniting them, adding even more carbon dioxide to the atmosphere. Could an industrial civilization have existed and been wiped out by the same catastrophe? Could their carbon emissions have been part of the mix? It's possible, but there's no evidence for it. The Siberian traps explain everything without needing to invoke a civilization. And again, the timescale is wrong. The extinction took hundreds of thousands of years. Industrial collapse happens in decades to centuries. So no, there probably wasn't a civilization during the end Permian. But it's an example of how complex these events are and how many factors can contribute to environmental catastrophe. One more, the Cretaceous-Paleogene boundary, the KPG event, 66 million years ago. The dinosaurs go extinct, along with about 75% of all species. We know what caused it. A 10-kilometer asteroid slammed into what's now the Yucatan Peninsula in Mexico. The impact energy was equivalent to billions of nuclear weapons. It vaporized rock, threw debris into the atmosphere, caused global fires, and blocked out the sun for months or years. Plants died, herbivores starved, carnivores starved. It was a disaster of unprecedented scale. But here's a weird thought. What if there was a civilization, and they saw it coming? What if they tried to deflect the asteroid and failed? What if they built bunkers and shelters, trying to survive the impact winter, but couldn't? Their bunkers would be buried, destroyed by the impact and subsequent geological activity. Their warnings, their technology, their attempts to save themselves, all of it erased. All that's left is the asteroid impact and the extinction. We'd never know they were there. This is pure speculation. There's zero evidence for a KPG civilization. But it's a haunting thought. That intelligence might have arisen just in time to witness its own annihilation. And that we'd never know because the event that destroyed them was so catastrophic that it erased every trace. These examples show the challenge of the Silurian hypothesis. Earth's history is full of catastrophic events. Impacts, volcanism, climate shifts, extinctions. Any of them could have destroyed a civilization. And any of them produce signatures that obscure or mimic industrial activity. So even if we wanted to find evidence of ancient civilizations, we'd have a hell of a time distinguishing it from all the other crazy stuff that's happened on this planet. Let's think about intelligent life more broadly. We know intelligence has evolved on Earth at least once. That's us. But how likely is intelligence? Is it an inevitable outcome of evolution, given enough time? Or is it a rare fluke, a cosmic accident that happened once and might never happen again? We don't know. We'd like to think intelligence is common because that makes us feel less alone. And there are arguments for it. Evolution tends to favor traits that improve survival and reproduction. Intelligence is useful. It lets you solve problems, adapt to new environments, cooperate in complex ways. So you'd expect natural selection to favor it. And we do see cognitive complexity evolving independently in multiple lineages. Primates, cetaceans, elephants, corvids, parrots, octopuses. That suggests intelligence is a convergent solution, something evolution discovers repeatedly. But there's a counterargument. Intelligence is expensive. Brains require a lot of energy. Human brains are about 2% of body weight but consume 20% of our energy. That's a huge investment. And for most of Earth's history, intelligence wasn't necessary. Simple organisms, bacteria, algae, plants, they do just fine without brains. They've been thriving for billions of years. Complex intelligence might only be advantageous in very specific circumstances. Social species that benefit from cooperation. Species that use tools. Species in variable environments where adaptability is key. If those circumstances don't arise, intelligence doesn't evolve. And even when intelligence does evolve, it doesn't necessarily lead to technology. Dolphins are smart, but they can't build fires. Octopuses are smart, but they're solitary and short-lived. Elephants are smart, but they're grazers without much need for complex tools. Humans are a very specific combination of traits that came together in a very specific environment. If any of those factors had been different, we might not have developed technology. And if we hadn't, some other species might have, or maybe no species would have. We don't know. So the question of how often intelligence arises is open. It could be common. It could be rare. We have one data point, and you can't draw a trend line from one point. But let's assume it's reasonably common. Let's assume that over Earth's long history, intelligence has evolved multiple times. Not in every epoch, but occasionally. Once every 100 million years, say. That gives us a few opportunities over the last 600 million years. Maybe one in the Cambrian, one in the Devonian, one in the Carboniferous, one in the Mesozoic, one in the Cenozoic. Each time, a species gets smart, develops culture, maybe even technology. And each time, something happens. Climate change. Disease. Competition with other species. An asteroid. They go extinct. And the geological clock resets. If this happened, would we know? Based on everything I've said, probably not. The evidence would be too degraded. We'd find their fossils and not recognize them as intelligent. We'd see chemical anomalies and attribute them to natural causes. We'd miss the clues because we're not looking for them or because they're too ambiguous. But here's an interesting thought. Maybe we wouldn't miss them. Maybe we've already found them and misinterpreted them. There are anomalies in the fossil record, things that don't quite fit our understanding of evolution. The Cambrian explosion, for example. 540 million years ago, complex multicellular life suddenly appears and diversifies rapidly. In a few million years, you go from simple worm-like creatures to a huge variety of body plans. Arthropods, mollusks, echinoderms, chordates, all of them appearing seemingly out of nowhere. It's one of the great mysteries of paleontology. The standard explanation is that it wasn't really sudden. It just looks that way because the fossil record is incomplete. Precambrian fossils are rare because early animals were soft-bodied and didn't preserve well. Once hard shells and skeletons evolved, fossilization became easier, and suddenly we have a rich record. So the Cambrian explosion is partly a real event and partly a preservation artifact. Animals were diversifying before the Cambrian, but we don't have the fossils to prove it. But what if it was something else? What if there was intervention? Not aliens, necessarily. But maybe an earlier intelligent species, a Precambrian civilization, that genetically engineered life, experimented with different body plans, and created the diversity we see. It's wild speculation, but it fits the evidence as well as the standard explanation. You'd need to find other evidence, artifacts of this hypothetical civilization, to make the case. And we haven't. so it's almost certainly not true. But it's an example of how ambiguous the evidence can be. Or consider the Permian-Triassic transition. After the end Permian extinction, life took millions of years to recover. But when it did, reptiles diversified rapidly. Dinosaurs appeared. Mammals appeared. Pterosaurs, marine reptiles, all kinds of new groups. It's like evolution was experimenting, trying out new forms. Could there have been a guiding hand? Again, probably not. Natural selection explains it just fine. But the point is, when you start looking for evidence of ancient intelligence, you can find patterns that could maybe, possibly, if you squint, fit the hypothesis. And that's how pseudoscience gets started. That's how you end up with ancient astronaut theories and lost Atlantises. People see patterns, jump to conclusions, and ignore more mundane explanations. The Silurian hypothesis, as formulated by Schmidt and Frank, is not that. It's not claiming ancient civilizations existed. It's asking how we detect them if they did. It's a scientific question with a scientifically rigorous answer. It would be very hard. And that's a legitimate and important conclusion. It tells us about the limits of the geological record and the challenges of reading deep time. But it also opens the door to speculation. And speculation is fun. It's how we explore ideas and push the boundaries of what we know. As long as we don't confuse speculation with evidence, as long as we stay grounded in science, it's a useful exercise. So let's speculate a bit more. If there were ancient civilizations, what happened to them? Why did they collapse? And could we learn from their failures? There are lots of ways a civilization can end. Let's go through them. Climate change. This is the big one for us right now. If a civilization industrializes, burns fossil fuels, releases greenhouse gases, it changes the climate. Temperatures rise. Ice caps melt. Sea levels rise. Weather patterns shift. Agriculture fails. There are droughts, floods, famines. Ecosystems collapse. Species go extinct. And eventually, the civilization can't cope. It fragments, it collapses, it reverts to a simpler state or goes extinct entirely. This has happened to human societies on a smaller scale. The Maya, the ancestral Puebloans, the Easter Islanders, all of them faced environmental crises that contributed to their decline. Climate change, whether natural or self-inflicted, is a civilization killer. An ancient industrial civilization would have faced the same risk. If they burned fossil fuels without understanding the consequences, they could have triggered runaway warming, ocean acidification, ecological collapse. And without the technology to mitigate it, they'd be doomed. Maybe that's what happened. Maybe every civilization makes the same mistake. They find fossil fuels, they industrialize, they grow, they prosper, and then they overshoot. They change the climate faster than they can adapt, and they collapse. It's a depressing thought. But it's a plausible one. Resource depletion. Civilizations need resources. Food, water, energy, materials. If you deplete your resources faster than they can regenerate, you're in trouble. Ancient human societies collapsed due to deforestation, soil erosion, overfishing, overgrazing. They degraded their environment to the point where it couldn't support them anymore. An industrial civilization would face this on a larger scale. They'd mine out their ores, deplete their fossil fuels, exhaust their aquifers. And once the resources are gone, the civilization can't sustain itself. It contracts, simplifies, collapses. This is another plausible end for a hypothetical ancient civilization. They industrialize, they grow, they consume, and eventually, they run out. Maybe they figure out renewable energy in time. Maybe they don't. If they don't, they collapse. And we'd never know because the evidence erodes away. War. Humans are good at fighting each other. We've been doing it for as long as we've existed. And the more advanced our technology, the more destructive our wars. An ancient civilization with advanced technology could destroy itself in a war. Nuclear weapons, biological weapons, chemical weapons, nanotech, pick your nightmare scenario. If they had the technology and the will, they could render their planet uninhabitable. Maybe that's what happened. Maybe they built weapons they couldn't control, and they wiped themselves out. All that would remain is a thin layer of radioactive ash and some weird isotope ratios. And after a few million years, even that would fade. Disease. Pandemics can devastate civilizations. The Black Death killed a third of Europe's population in the 14th century. Smallpox wiped out vast numbers of Native Americans when Europeans arrived. An ancient civilization could have been destroyed by disease, especially if they had global trade in dense cities. A pathogen evolves, spreads rapidly, kills most of the population. The survivors can't maintain the infrastructure. Society collapses. And again, the evidence vanishes. Disease doesn't leave a clear geological signature. You might see a sudden population decline in the fossil record, but you wouldn't know the cause. Asteroid impact. This is the wild card. Asteroids don't care about your civilization. They hit randomly, without warning, and they cause global catastrophes. If an ancient civilization existed and an asteroid hit during their time, they'd be wiped out along with everything else. The asteroid signature, the iridium layer, the shocked quartz, would obscure any evidence of their existence. We'd see the impact and the extinction and never realize there was a civilization there. Supervolcano. Massive volcanic eruptions can trigger climate change, block out the sun, cause famines and extinctions. The Toba eruption 74,000 years ago may have reduced the human population to a few thousand individuals. A similar event could destroy an ancient civilization. And the volcanic signature would, again, obscure their existence. We'd see the eruption and the climate change and think it was purely natural. Solar flare. The sun occasionally throws tantrums, ejecting massive amounts of charged particles into space. If a really big solar flare hit Earth, it could fry electronics, disrupt the power grid, cause widespread fires. An advanced civilization dependent on electricity could be crippled. And if they couldn't recover, they'd collapse. But solar flares don't leave much of a geological signature. We'd never know. Gamma ray burst. These are rare, but they happen. A nearby star goes supernova, and it releases a burst of gamma radiation that bathes Earth. The radiation would strip away the ozone layer, sterilize the surface, cause a mass extinction. If a civilization was unlucky enough to be around when this happened, they'd be wiped out. And there'd be no clear signature. Maybe some isotopic anomalies from the radiation, but nothing obvious. The point is, there are lots of ways to die. Lots of ways for a civilization to end. And most of them leave ambiguous or invisible signatures in the geological record. So if ancient civilizations existed and collapsed, we might not be able to tell why. We'd just see the aftermath. Extinctions, climate changes, chemical anomalies. And we'd interpret them as natural events because we have no reason to think otherwise. This is the humbling reality of the Silurian hypothesis. The past is largely inaccessible. We can read the rocks, but we can't read minds. We can see what happened, but not always why. And the farther back you go, the less you can see. Deep time is a fog that obscures everything. Shapes emerge, events, patterns, but the details are lost. The individuals, the stories, the struggles. All of it fades into silence. And that will happen to us too. If we collapse, if we disappear, future geologists will see our chemical signature. They'll see the carbon spike, the plastic residues, the radioactive isotopes. They'll see the extinction event we're causing. They'll piece together a story. But it won't be our story. Not really. It'll be a simplified, sanitized version. They won't know our names, our cultures, our hopes and fears. They won't know about art, music, literature, love. They'll just know that something happened here, something that changed the planet, and then it ended. Unless we survive. Unless we endure. That's the only way to preserve our story. To still be here, telling it. Let me come back to the science one more time. Because there's a specific technique that might, just might, be able to detect an ancient civilization if one existed. It's called chemostratigraphy. This is the study of chemical variations in sedimentary rock layers. By analyzing the chemistry of rocks, you can identify specific events, correlate layers across different locations, and reconstruct environmental conditions. For example, the KPG boundary, the asteroid impact that killed the dinosaurs, is marked by an iridium anomaly. A thin layer of clay enriched in iridium, found globally. Wherever you look, at the boundary between the Cretaceous and Paleogene, you find this layer. It's a clear marker. And it tells you something dramatic happened at that moment in Earth's history. Similarly, the PETM is marked by a carbon isotope excursion. A rapid shift in the ratio of carbon-12 to carbon-13, indicating a massive input of light carbon into the atmosphere and oceans. This signature is found globally in marine sediments. It's diagnostic of the event. If an ancient industrial civilization existed, it might leave a similar global marker. A chemical anomaly that appears suddenly, persists for a geologically brief time, and then disappears. The trick is knowing what to look for and distinguishing it from natural events. What specific markers would indicate industrial activity? Here are some possibilities. First, uranium isotope ratios. Natural uranium consists of about 99.3% U-238 and about 0.7% U-235. If a civilization enriched uranium for nuclear reactors or weapons, they'd alter this ratio. The waste products would have elevated U-235 levels, or more likely, depleted U-235 levels if they extracted it. This altered ratio could persist for millions of years and would be a clear sign of nuclear technology. The problem? Natural uranium deposits can have variable isotope ratios due to geological processes. And you'd need to find the specific site where the enrichment took place. Not impossible, but difficult. Second, plutonium isotope ratios. Plutonium doesn't occur naturally in significant amounts. It's produced in nuclear reactors. If you find plutonium in ancient rocks, especially in specific isotopic ratios like Pu-239 and Pu-240, that's a smoking gun. It has to be artificial. The problem? Plutonium's half-life is too short. After a few million years, it's gone. You'd need to look at relatively recent times, geologically speaking, to find it. And by recent, I mean less than 1 million years. And we've already studied that time period pretty thoroughly. We haven't found any plutonium anomalies. Third, carbon isotope spikes. As I've mentioned, burning fossil fuels produces a characteristic carbon isotope signature. An influx of light carbon, C12, from ancient organic matter. This shows up as a negative carbon isotope excursion in marine carbonates and terrestrial sediments. The problem? Volcanism, methane release, and other natural processes produce the same signature. You can't use carbon isotopes alone to prove industrial activity. You'd need additional evidence. Fourth, nitrogen isotope variations. Industrial agriculture, specifically the Haber-Bosch process, alters nitrogen isotope ratios. The synthetic nitrogen has a different N15/N14 ratio than natural nitrogen fixation by bacteria. If you found sediments with anomalous nitrogen isotopes, it could indicate industrial agriculture. The problem? Nitrogen cycles rapidly through the environment. The signal would be smoothed out and lost relatively quickly, within millions of years. Fifth, rare earth element patterns. Rare earth elements, REEs, are used in electronics, magnets, batteries, all kinds of high-tech applications. We mine them and concentrate them in our products. When those products degrade, the REEs are released into the environment in patterns that differ from natural geological distributions. If you found sediments with anomalous RE patterns, it could indicate industrial activity. The problem? REE patterns vary naturally due to weathering, hydrothermal activity, and other geological processes. You'd need to distinguish anthropogenic patterns from natural ones, which is tricky. Sixth, synthetic molecules. If a civilization created durable synthetic compounds, polymers, or materials that don't degrade easily, those might persist in the geological record. You'd be looking for organic molecules with structures that couldn't be produced by known biological or geological processes. The problem? Identifying such molecules requires extremely sophisticated analytical techniques. And even if you found them, you'd have to rule out contamination and unknown natural synthesis pathways. It's possible, but it would be very challenging. So even with advanced chemostratigraphy, detecting an ancient civilization is difficult. You'd need a combination of markers, a consilience of evidence, all pointing to industrial activity. And you'd need to rule out natural explanations. That's a high bar. But it's not impossible. If we applied the full arsenal of modern analytical techniques, isotope geochemistry, organic geochemistry, trace element analysis, to the systematic study of potential industrial signatures in the geological record, we might find something. Or we might conclusively demonstrate that there's nothing to find. Either way, it would be valuable science. And this is, in fact, what Schmidt and Frank were advocating. Not that we should go searching for ancient lizard people. but that we should think more carefully about what markers an industrial civilization leaves and how long they last. Because that tells us about our own legacy. It tells us what we're leaving behind. And it might inform our choices going forward. If we know that our industrial activity will be detectable for millions of years, that puts a different spin on what we're doing. We're not just affecting the present. We're affecting the deep future. We're writing our story into the rocks. And that story is, currently, one of rapid environmental change, mass extinction, and geochemical disruption. Not a great legacy. But we could change the story. We could transition to sustainable energy, stabilize the climate, protect biodiversity, and leave a different signature. One that says we were here, we were intelligent, and we chose wisely. That would be a legacy worth preserving. That would be a story worth telling. So the Silurian hypothesis isn't just about the past. It's about the future. It's about understanding that our actions have consequences that extend far beyond our lifetimes, far beyond our civilizations, into the deep geological future. And that should make us think very carefully about what we're doing and why. Let me end with a thought experiment. Imagine you're a geologist 10 million years from now. You're a member of a species that evolved after humans either went extinct or left Earth. You're digging through rock layers, trying to understand the history of your planet. You come across a thin layer of sediment from the late Holocene, what we call the present day. You analyze it. You find elevated carbon dioxide, plastic residues, radioactive isotopes, elevated concentrations of metals, synthetic organic molecules. And you find evidence of a mass extinction, a sudden loss of biodiversity. What do you conclude? Do you recognize it as the signature of an industrial civilization? Or do you think it's a natural catastrophe, a volcanic event or an asteroid impact or a climate shift? How do you tell the difference? You'd probably look for physical artifacts. You'd excavate, hoping to find structures, tools, remains of organisms. And you'd find nothing. Everything's gone. Eroded, subducted, recycled. So you're left with the chemistry. A constellation of anomalies. Strange but not inexplicable. You'd probably debate it. Some of your colleagues would argue for a civilization. Others would argue for natural causes. And you'd never know for certain. You'd never be able to prove it. Because the evidence is ambiguous and incomplete. And then you'd think, are we the first? Or did this happen before? Is this a pattern? Does intelligence arise, industrialize, collapse, and disappear, over and over, leaving only faint traces in the rocks? And you'd look deeper, searching older rocks for similar signatures. And maybe you'd find them. Or maybe you wouldn't. But the question would haunt you. The uncertainty would gnaw at you. Because you'd realize that you might not be the first, and you might not be the last. That this is a cycle, a trap that civilizations fall into again and again. And you'd wonder if your own civilization is doomed to the same fate. That's the Silurian hypothesis. It's a mirror and a warning. It shows us our impermanence. It shows us that intelligence is no guarantee of survival. That technology can be a double-edged sword. That the universe is indifferent to our existence. But it also shows us that we have a choice. We can learn from the past, even if that past is hypothetical. We can recognize the dangers and act to avoid them. We can build a civilization that lasts, that endures, that doesn't become just another ambiguous layer in the geological record. The question is, will we? Will we make the right choices? Will we stabilize our climate, protect our biosphere, expand into space, and ensure our long-term survival? Or will we collapse, fragment, and vanish, leaving future geologists to puzzle over our remains? I don't know the answer. Nobody does. But I know this. The clock is ticking. Geological time is patient. It will wait. But we can't. We have to act now. We have to decide what kind of legacy we want to leave. Do we want to be a mystery? An unsolved riddle in the rocks? Or do we want to be here, still thriving, still learning, still reaching for the stars, when the next intelligent species evolves and asks, are we alone? I know which future I'd choose. The universe is vast. The earth is old. Life is tenacious. Intelligence is rare but possible. And civilizations are fragile. All of these things are true. And they all point to the same conclusion. We're not guaranteed to survive. Our existence is contingent on choices we make every day. Choices about energy, about consumption, about how we treat our planet and each other. And those choices will determine whether we endure or whether we become just another layer in the rocks, just another spike in the carbon isotopes, just another extinction event to puzzle future scientists. The Silurian hypothesis asks, are we the first? Maybe we are. Maybe we're not. But more importantly, it asks, will there be others after us? Will life go on? Will intelligence arise again? And will that future intelligence look back at our time and see evidence of wisdom? Or evidence of folly? The answer is up to us. The rocks will remember. They always do. They'll record our choices, our triumphs, our failures. They'll tell our story to anyone who knows how to read them. The question is, what story do we want to tell? I hope it's a good one. I hope it's a story of a species that woke up, that realized what it was doing to its planet, and that changed course. That developed sustainable energy, protected its biosphere, expanded into space, and became a multiplanetary civilization. That survived its adolescence and matured into something enduring. That left a mark not of destruction, but of creation. Not of extinction, but of preservation. Not of endings, but of new beginnings. That's the story I want to see written in the rocks. That's the legacy I want us to leave. But we're running out of time. The geological clock is ticking. And unlike the civilizations we imagine in the Silurian hypothesis, unlike those hypothetical lost societies that vanished without a trace, we have something they didn't. We have knowledge. We have foresight. We have the ability to see the danger and change course. We know what we're doing to the planet. We know the risks. We know the consequences. And we have the technology to do something about it. So the question is not whether we can survive. The question is whether we will. Whether we'll make the hard choices, the necessary sacrifices, to ensure our long-term future. Whether we'll be wise enough, brave enough, compassionate enough to build a civilization that endures. A civilization that future geologists won't just find evidence of, but will meet face to face and learn from. That's the challenge. That's the test. And it's happening right now. Not in some distant future. Not in some hypothetical scenario. Right now. Every day. With every choice we make. The Silurian hypothesis started as a simple question. If an ancient civilization existed, would we know? And the answer is maybe not. But it evolved into something deeper. A meditation on time and memory and legacy. A reminder that we're part of a continuum, a chain of life that stretches back billions of years and could continue for billions more. Or could end with us. We get to decide. And that's the most important thing to understand. We're not passive observers. We're not victims of fate. We're active participants in our own story. We're writing it right now, every day, with our actions and our choices. And the rocks are watching. The geological record is building. The evidence is accumulating. Future geologists, human or otherwise, will read it and make their judgments. What will they find? Evidence of wisdom? Or evidence of a species that had every opportunity to save itself and chose not to? Evidence of a civilization that thrived for millions of years? Or evidence of a brief, brilliant flash that burned out and vanished? It's our choice. And the clock is ticking. This has been an exploration of the Silurian hypothesis. Not a claim that ancient civilizations existed. Not a conspiracy theory. But a scientific thought experiment that reveals the limits of our knowledge and the fragility of our existence. It's a question about the past that's really a question about the future. It's a warning wrapped in a mystery. And it's one of the most important questions we can ask. Are we the first? Maybe. Probably. But definitely not guaranteed to be the last. Unless we fail. Unless we collapse. Unless we become just another question mark in the rocks. I don't want that to be our fate. I want us to endure. I want us to thrive. I want future geologists to find clear, unambiguous evidence of our civilization and to meet us, still here, still thriving, still learning. I want our story to have a happy ending. But that's up to us. All of us. Every choice. Every day. The rocks are watching. And they'll remember everything. So let's make it a story worth remembering.